Hi everyone, this is Billy. Some of you may know that I've created a 3D designed chassis for another AM, FM crystal radio. So I'm breaking down the radio into multiple parts. This part talks about the circuit itself. First, let's talk about the FM circuit. I will show you the actual parts while you look at this circuit. So this is the two different part of my crystal radio. This one I'm holding now is the FM part, and this is the AM part, medium wave. So let me go through the FM part, which is simpler. The most important component of this FM crystal radio is this air variable capacitor, and it's made of copper. There's only 3 moving plates, 3 fixed plates, and it can change the capacitance from around 5 pF to around 15 pF. So if you've got more capacitance, what you can do is either remove the plates to less plates, so you can get a smaller variable capacitance that suits the coil here, or you can change the coil to a smaller diameter or less number of turns. Now let's look at the coil. There are 1, 2, 3, 4, 5, 6 turns altogether in this coil. The first turn is for connecting to the antenna, which is this brown wire here. The antenna will ultimately be connected to this screw on the chassis named FM1. This screw. So we have some solder there already. We'll just solder it directly. So this is the first turn for the antenna. And then after the first turn, it is the ground of the circuit ground. So the circuit ground connects to this moving plate terminal of the variable capacitor. It is such that when you touch it, it won't affect the circuit and make it silent. Otherwise, if you connect to here, when you turn the circuit, what we call the hot part of the coil will be influenced, and then you got no sound from the radio. Okay, so remember, connect the grounding point of the circuit always to the moving plates terminal. Then after the first turn, we go to the second turn. Second turn, we have another wire for the connector, and this wire will be connected to the FM2 screw. It's an M4 screw. So this screw we can hook up, will connect to the telescopic antenna, which has an M4 screw hole. So you can just install the antenna later. Okay, and besides the antenna connection, the second turn also have another function, which is connecting to the detector. So the detector that we can use for the crystal radio, the FM crystal radio, includes the MOSFET, the MOSFET. I'm using the 3DQ, 3SK143-Q. Okay, so you see it's a very tiny circuit mounted board that I have to connect to a bigger circuit board, connect to this 4-pin header here, the male header here, and in turn I will plug it into this female header like this. Okay. The other choice of your FM detector is a regular diode. Not every diode will work. Those diodes with a very high junction capacitance cannot work because it will influence the FM frequency. So you have to find the diode with a very small junction capacitance. I have been using detectors like 1S86 or 116 or 1S91 something. So you can try those diodes. Also HSM 8520 will work. 1N34A will also work. May also work. 1N60 may or may not work. Crystal may or may not work depending on your junction capacitance of that crystal and your cap whisker. But I've been successfully tried to use a crystal to drive an FM detector, which barely audible. I know it's connecting and it's detecting, but I can't hear exactly what the radio broadcast is saying. Music is fine, but audio from conversation is not really recognizable. So this detector for coil turn number 2 connect to this orange wire and into this socket, so you can put in the right detector of your choice. Okay. So now we go to the third turn. The third turn is connecting to this green wire, which is also can be used for detector. So either the second turn or the third turn can be used to connect to the detector, depending on the impedance matching of the coil of the resonance circuit and the diode, right? Sometimes the second turn will work better, sometimes the third turn or the middle of the coil will work better. So you have to try it out. Insert your diode into the different pinholes here to try which one works. Okay. And then the ring continue to the last turn, which is called the hot end, which connects to the fixed plate of the variable capacitor. So what kind of wire you can use to make this coil? You can use regular copper wire, at least 1 millimeter thick. I've tried to use thicker wire. It will give you a higher volume output. That means sensitivity will increase, but then selectivity will decrease. Also, the clarity of the broadcast will decrease as well. It kind of insert more noise if you use a thicker wire. Okay, so try to test with different thickness of the wire and you can experience different things. Okay, so then we'll talk about the different the other connection from the hot end of the coil and the fixed plate of the variable capacitor is to this white wire here. And this white wire actually connects to one pin of the MOSFET detector. So that pin is called the G2, gauge number 2. Okay. So gauge number 2 in my MOSFET circuit for crystal radio always connect to the hot end of the coil, no matter how many turns you have. And then on the other hand, the grounding point of the circuit, which is this brown wire here, which also connects to the moving plate of the variable capacitor, also connect to second turn of the coil. That connection, the brown wire connects to gauge number 1, G1 of the MOSFET. Okay, in my MOSFET circuit that I use for AM, FM, shortwave, gauge 1 always connect to the grounding point of the circuit, which is this brown wire. Okay, so the remaining two pins of the MOSFET is the D, the drain, and the S, the source. The drain pin here is this this blue wire here, which is next to the gate number 2. This blue wire that I'm touching. And this blue wire is the output of the detector circuit and is connected to the audio jack. I'm using a 3.5 millimeter audio jack. And it's a stereo jack, but I'm using it in a mono way. I just use one of the two. I use the tip of the audio jack. Okay, the other side of the audio jack we connect to the grounding point of the circuit, which is this brown wire. Also, in order to filter out the high frequency and make the crystal radio efficiency higher, so we can harvest back all the DC signal, there is a small capacitor that matches the frequency of the signal that we are detecting. So this one is around 150 pf. So between 100 to 180 or 200 pf you can try. 150 pf is fine for this type of frequency. Okay, but if you are using it for the AM circuit, you need a higher capacitance, like 4.7 NF. Yeah, 4.7 NF. That means 4,700 PF. But for FM, we're using just 150 PF, picofarad. Okay. And the last pin of the MOSFET detector, which is this orange wire, it connects to the second turn of the coil. Okay, so as I said before, this can be also used for the diode, right? Okay, so if you want to use a diode instead of the MOSFET for detector, what you do is one end of your diode always plug into this hole which connects to the blue wire for the output. The other end of the diode, depending on your impedance matching need, you can connect to the pinhole where the orange wire is. That is the second turn of the coil, which is a lower impedance. Or if you want a higher impedance, you connect to the green wire, the pinhole going to the green wire, which is this one. That will give you a higher impedance. If you even want a much higher impedance, you can directly connect it to the white wire, the pinhole of the white wire, which connects to the hot end of the coil, right? So by changing the different position of connection, that we also call it tapping point of the coil, you can change the impedance to match between your diode and the resonance circuits. So you need to try and see which one works better. But in general, the closer to the hot end of the coil where you connect your diode to, the higher will be the sensitivity. But the lower will be the selectivity, and lower will be and then there will be a more noisy reception. Okay. As you move closer to the grounding point of the circuit and the coil, which we also said is the cold end of the coil, then sensitivity will decrease, but selectivity will increase, and the clarity of the signal will increase. So you have to try it out and see which one works. Okay. So I think that's it about the FM circuit. You can see this. I find this variable capacitor a better one than the other one because the size is small and you can turn it very smoothly. So it allows you to make a small FM crystal radio with a good quality. Okay, and what else I can say? The other thing you need to be careful about is all this connection between the components, especially the resonance circuit itself, between the capacitor, the variable capacitor and the coil. It must be soldered directly between the component. You shouldn't use this type of thin wire to interconnect the coil with the variable capacitor or make it longer than, I think, 1 inch. Yeah. So this wire should not be longer than 1 inch. Otherwise, you will find that the length of the wire will add into the frequency, influence to the frequency itself. So that means the longer the wire, your frequency of the resonance circuit will drop to a point where it falls outside the FM frequency spectrum, right? We don't want that. So you have to keep your connecting wire within 1 inch between the variable capacitor and the coil. The second point is it must be soldered directly. Don't twist and make the connection, because the resonance circuit is the most important part of your crystal radio. it will make or break your crystal radio, especially the FM crystal radio. So the soldering must be clean, shiny, and solid. Okay, so you may need to have a higher power soldering gun. Otherwise, you may not be able to melt the solder and stick it cleanly to your connection points. Okay, the other point is this coil, because I need a very firm connection of the grounding point of the coil to the variable capacitor. I have two pieces of wire. One piece make up the most of the coil, most turns of the coil. The other one just is used for this one turn, and then I twist them together and then connect them to the moving plate of the variable capacitor. This way is firmer. The alternative is you use one piece of wire for the second turn of the coil and then immediately solder that directly to the moving plate of the variable capacitor. And then at this joint, you try to solder another wire just to create that one turn for the antenna. But this way is not very secure because that connection will be very weak. That soldering will be very weak, and it may break if you try to adjust the coil later on. Because after we make it, we may find your FM range falling outside too much of the FM spectrum, and then you may want to squeeze or pull your coil to adjust it, right? You can adjust it like that, make it longer or make it shorter. If you make it shorter, the frequency will decrease. The frequency spectrum will go to the lower end. Right? If you lengthen it, the frequency will be decreased. Yeah. So depending on what you are doing with your coil, right? So the coil must be securely soldered. Okay. So that's enough about the FM crystal radio. Next, let's look at the AM circuit. First, let's look at the resonance circuit. So the resonance circuit contains the variable capacitor. In this case, this is a plastic variable capacitor, but this one is specially manufactured in Japan, so it's considered higher Q factor than the other ones created in China. Also, this coil is a ferrite core coil, and it's a ring, and the ring is manufactured in China. It has a special product model that is designed by the crystal radio hobbyists in China. So they find a factory to create this and make this a very high quality, high Q factor core that you can use to make both AM and shortwave radios. So I put a layer of insulation on top of the ferrite core. I used the tapes for repairing the water pipes. I think it's called silicone tape, multiple turns, because there's a saying that those tapes will not affect the quality of the coil. Okay, and then I use the list wire. List wire is a special type of wire that includes hundreds of tiny insulated copper wire in each thread. So like this one, right? I have removed the stiff, and then you can see this tiny wire. They are all insulated like magnet wire, but they are put together to create a very high quality coil because it increases the surface area of compared to the same thickness single core wire. So this is a multi-core wire. For this one, I think it's around 100 threads, I forgot what it is, 120 frets. Yeah, the list wire I'm using. So it's 120 frets. Each fret is around 0.04 millimeter in diameter, so very tiny. But to add up together, it will form a very high Q factor coil. And I wound a number of turns. You can look at the circuit diagram to see exactly how many turns. I think it's around 60 turns or 55 turns. I think it's 55 turns. And then in addition, I put in another 5 turns to use as the antenna coil. That means the coil connecting directly to the antenna, and as the detector coil for the MOSFET, which need a separated coil to fit to the source pin of the MOSFET. Okay, so there's how many wires? 4 wires coming out from this coil. Okay, so let me show you which one by one. Okay, so this wire is the circuit ground of the coil, that means the co-end. This wire is the extra 5 turns that is used to fit to the source pole of the MOSFET. Also will be used as the connection to the antenna to match the impedance of the antenna. External antenna, or I mean. And this other wire, this one, is the hot end of the coil. That means the last turn of the coil. I think the 55th turn. Okay. This wire is the number of turns equivalent to 1/3 of the total number of turns, counting from the cold end of the coil, which means the grounding point of the circuit. So 1/3 of the total number of coil, which will kind of match a lot of the different diodes impedance. Okay, so for this one is for diode connection, and this one extra 5 turns from the cold end of the coil is for the MOSFET source pole connection. Okay, and of course the cold end of the coil and the hot end of the coil in turn connect to the moving plates of the variable capacitor, which is also the grounding point of the circuit. And the hot end of the coil will connect to the fixed plate of the variable capacitor, which is this one. Okay, this one is a very old variable capacitor that I harvested from the old crystal radio, because it's very hard to buy this type of high quality, high Q factor variable capacitor manufactured in Japan anymore. I've been searching on the online shopping site in China. I couldn't find any more. It's very huge compared to the other plastic variable capacitor, which is usually 1/3 the size or half the size, right? So that's why it's very high quality. Okay, and there is also additional trimmer here to allow you to change the variable capacitance range a bit, but I decided not to use it because it will lower the entire Q factor of the whole resonance circuit if you attach more components. So I try to keep the components to a minimum, including the number of variable capacitors. Okay, so as I said, I'm using the MOSFET as the detector, but you can also have a choice to use the diode as a detector. Just put it into the right pinhole, and I'm going to show you. Okay, so this is the socket for the detector. Pin 1 of the socket is this brown wire, which connects to the circuit grounding point, also to the fixed plate of the variable capacitor, also to the cold end of the coil. So this is, if you use a MOSFET, this will connect to the gate 1 of your MOSFET. So this is the MOSFET. It comes in a surface mounted device type. So you need to connect it to a bigger circuit board and then connect it to this 4-pin socket, which can plug into this 4-pin female socket. Okay. So gate 1 is this one, this point in the MOSFET. And then the fixed plate of the variable capacitor, also the hot end of the coil, which is this white wire, will connect to the gate number 2 of this MOSFET, which is this pin here. Okay. The orange wire here represent the source pole of the MOSFET, which is the one here, second pin here. The source pole will connect to the extra 5 turns after the grounding point of the circuit, after the cold end of the circuit. Right, this way the source pole will get some voltage to drive the earphone, but because it's outside of the resonance circuit's extra 5 turns, that means the pull and influence to the resonance circuit will be much reduced. So that's why this is extra 5 turn instead of taking the 5 turn within the resonance circuit, within the resonance coil as a tapping point. Both will work, but if you try it later, you'll find extra 5 turn will be getting you a much clearer output and much louder output. Okay. And the other pin here, which is this blue pin, will connect to the audio jack for the output, which is this blue wire. The blue wire connects to the audio jack. The other end of the audio jack connects to this brown wire, which is also connecting to the grounding point of the circuit, to the moving plate of the variable capacitor, and to the cold end of the coil. Okay. So in order to filter out the high frequency and keep the DC component of the output signal circulating in the circuit to increase the efficiency, we will have the filter capacitor. Because it's AM, frequency is lower, the filter capacitor value is 4.7 nanofarad, which is 4,700 picofarad. Okay. It's 4,700 PF, okay, or 4.7 NF. Okay, what else I need to talk about? Okay, because I want to make this circuit flexible, so you can change it to an AM crystal radio to an FM to a short wave crystal radio by changing the coil, keeping the variable capacitor. So that's why I put in a terminal block to connect to the wire of the coil indirectly rather than directly soldering to the variable capacitor. I know that this will lower the overall Q factor of the resonance circuit, but I think it's more flexible for me because I may also be using this let me show you. This big loop ring coil, which has only 7 turns, hanging on my window to listen to the radio at night without dropping a long wire through my window as the antenna. So that's why I need to be able to switch between this small farad coil and the big loop antenna coil. So that's why I use this terminal block. So there's only 4 pins of the terminal block. Okay. The pin 1, this one, where you find the blue and red interlaced color wire, is the extra 5 turns that connect to the source pole of the MOSFET. The second pin is the circuit ground of the circuit, the cold end of the coil. The third pin is connecting this one with a interlaced red and white color wire. It's connecting to the middle, the 1/3 of the coil. So this one, which is suitable for impedance matching with a diode. And of course, you can try out different turns to match your diode. You just solder it onto this wire and connect it into this pin. So you can use it for hooking up the diode. Okay, and in the socket, the connection to the diode pin is this green wire. So if you want to use diode as a detector, put one pin of your diode here and another pin of your diode into the hole connected to the blue wire here for the output. Okay. And the last one of the terminal block, this one without any coloring, this one connects to the hot end of the coil, which is this wire, hot end of the coil. Okay. So I forgot about the antenna connection. Okay. So we have 3 wires for the antenna connection. Let me show you. Okay, so these are the 3 wires. Okay, the first wire connects from hot end of the coil or the fixed plate of the variable capacitor. So this one is for you to use the antenna, telescopic antenna, which is quite short. Okay. Then you have the second antenna connection, which is connecting to this orange wire, which is also the source pole of the MOSFET, also the extra 5 turn after the cold end of the circuit. That means this one you can connect to a longer antenna. Of course, if you need an antenna tuning circuit, you need to add it another variable capacitor or another coil to match even longer antenna. But in general, you can use this pin for connecting to your external long antenna. Okay. Then if you want to connect to the earth or the grounding point of the earth at home, then you can use this brown wire. What I do at home is I find the water pipe which goes into the earth and connect a wire to my water pipe and extend it to connect to this pin here, the brown wire, which is the cold end of the coil and the circuit grounding point of the whole resonance circuit. I added a band switch to the resonance circuit. So the band switch works by whether shortening or opening the connection between the 2 fixed plates, which is this one and this one. Okay, by closing the switch, the 2 fixed plates are connected. That means you got double the amount of variable capacitance. So for my variable capacitor, each gain is around 350 pf. So if I double them up, it will become 700 pf. This is required for my big loop antenna, which has a lower inductance compared to the ferrite coil. So it needs 2 gauge connecting together to make it work, to make it tune to the lower end of the AM frequency spectrum. Okay, and the reason why we keep the number of turns in the loop antenna to a small one is because the loop antenna doesn't function well if you have too many coil, or the coil are too close together, and it also won't work well in the high frequency range if you just use a single band variable capacitor. So that's why I always need to break it into 2 bands, high frequency band and the low frequency band, for a loop antenna to function well, to cover both sides, both ends of the frequency spectrum. Well, that's the end of this part of the video. To follow on, watch my part number 3, installation and testing. I hope you can support my video by clicking like, subscribe, leave a comment and share with your friends. See you later.